Hello everyone, I'm presenting the work entitled Randomized Quasi-Monte Carlo for Efficient Fourier Pricing of Multi-Asset Options in Lévy Models, joint work with Christian Bayer, Shihab Ben Hamouda, Antonis Papapantoleon, and Raoul Temponen. So to summarize, the high smoothness of the integrand in the Fourier space motivates employing quadrature methods that are highly efficient under regularity assumptions, namely randomized Quasi-Monte Carlo. However, the addressed integrand is defined on the unbounded domain RD, which requires transformation to the hypercube, which oftentimes leads to integrands that are unbounded or have large derivatives near the boundary of the hypercube and no longer satisfy the assumptions of the Cox-Mahlavka inequality, which deteriorates the rate of the randomized Quasi-Monte Carlo. So in this work, we propose model-specific domain transformations and derive appropriate conditions on the mapping parameters to ensure and improve the convergence of the randomized Quasi-Monte Carlo. So the multivariate Fourier pricing formula is given as follows: as a d-dimensional integral of the characteristic function shifted by damping parameter to ensure it's well defined times a conjugate of the Fourier transform of the payoff function, which is also shifted by the same quantity, according to a rule that we proposed in previous work to make this integrand smoother. So in the setting, we consider two payoff functions, namely basket put options and column main, for which the functions in the physical space are given on the left, and their corresponding conjugate of Fourier transform is given as the following formula and defined for the imaginary part with these conditions. And for asset dynamics, we consider geometric Brownian motion, variance gamma, and normalized Gaussian, for which the characteristic functions are given as follows in this table 1. We have a Gaussian function for the GBM, we have a fractional function for variance gamma, and we have a root exponential for the normalized Gaussian. So the challenges of this work is that product rule quadrature methods suffer from the course of dimensionality. Hence, we propose using randomized Quasi-Monte Carlo to alleviate this course of dimensionality. The domain transformation also may introduce singularities at the boundary. Hence, we derive conditions on the parameters of the inverse CDF mapping to control the growth of the transformed integrand near the boundary. Essentially, this is our original integrand of interest over RD. We do the following change of variable, and we also, which means that we now have a different integral over the hypercube, where capital C minus 1 is the inverse CDF and lowercase small letter c is the corresponding probability density function, and capital lambda is the vector of parameters that you're using. So the randomized Quasi-Monte Carlo estimator is given as follows, as this double sum, where we have these QMC points shifted in order to obtain an error estimate. And the idea behind our proposed domain transformation is that the decay of the integrand is controlled by the characteristic function. Hence, we propose density to follow the same functional form, and which select its parameters in a way that we control the singularities at the corners of the hypercube of the transformed integrand, and we also impose product form form on the multivariate density to be written in the product of density, so we can have multivariate inverse CDF can be evaluated as the component-wise inverse CDF. So we choose a Gaussian for GBM, we choose t-student distribution for variance gamma, and we choose the Laplace distribution for normalized Gaussian with the corresponding conditions. And now we show a little bit of numerical experiments. So as you can see on the top left, there is this this is the original integrand, this is transformed integrand. As you can see that it is unbounded near the boundary. This is with shift, this is the transformed integrand, different parameters of the mapping. Now it is bounded but very heavy-tailed, and now it is already similar to the original integrand, a little bit spikier, of course, about the origin because we compressed the integrand. You also observe the effect of this domain transformation on the rate of convergence, but also implied constant of the randomized Quasi-Monte Carlo for the following examples. And you can see that if we take examples, which is, for example, here 5, which satisfies our conditions, we can get the optimal rate of Quasi-Monte Carlo, but you also get much better implied constants. And we also show substantial computation gains of the randomized Quasi-Monte Carlo compared to Monte Carlo, about 1,000 times more rapid convergence for the randomized Quasi-Monte Carlo compared to the Monte Carlo applied in the physical space. These are the references, and thank you for your